Hi students. In today's lesson, we will be going through the answers for Chemical Bonding Worksheet 1. And this worksheet, we will be focusing on ionic bonding. So let's begin the lesson. Okay, so if you look at the first part of the question, question 1 says complete the following table. So you notice that in this table there are two parts to it. The left hand side we are looking at atoms and right hand side we are looking at ions, right? So this part on atoms you should bring to your memory chapter 5, atomic structure, which is just before this chemical bonding chapter, right? So for atoms, we know that there are two relationships which are very important for this particular particle, right? And in atoms, the number of protons are equals to number of electrons. Okay, protons are positively charged, electrons are negatively charged. So if I have the same number of positive charge and negative charges, that's why we say that atoms they are electrically neutral. Okay, so a bit of recap here. And the um, second relationship will be that the nuclear number or mass number is equals to the number of protons plus the number of neutrons in the nucleus of an atom. Okay, so with that as prior knowledge, then that would make our lives easier to do this question. Okay, so if you notice, using the first relationship, you can also see that over here, the proton number and electron number of atoms are the same, right? Just as we have just gone through. And let me just change my ink color. Then, yeah. So make good use of this little trick that we have taught you in class, right? For instance, if you look at sodium, okay, instead of counting the electrons to figure out the electronic configuration, a very quick way is to use the group number as well as period number to help you with that. Okay, so for instance, sodium, we know that it is a group 1 metal. So, and then the period number is period 3, right? So you know from group 1, it will definitely have one valence electron right there, and it will have 3 electron shells because it's in period 3. Okay, you do the same for the rest and you should get the answer pretty quickly. So now let's look at ions. Okay, so in forming an ion, the general rule is that our metals, which is on the left hand side of the periodic table, they will lose electrons to form positively charged ions called cations. And then our non-metals, which are on the right hand side of the periodic table, they will gain electrons to form anions, negatively charged. Okay, so which is why ions as a type of particle, they are charged compared to atoms where they are neutral. Okay, so we see that in the answers also. For instance, let's say sodium, it has one valence electron. It will lose that one valence electron. So therefore, our number of electrons becomes 10. Same for magnesium. Magnesium is group 2, so it will lose 2 electrons. Aluminium group 3, it will lose that 3 valence electrons. So that's for metals, right? And then for non-metals, chlorine and oxygen, our examples here, okay, they will gain 1 electron and 2 electrons respectively. And that is how you get the answer in this final column. Okay, and you notice for the ions now, their electronic configuration, they all end with an 8, right? So in forming the ion, they would have achieved now the stable octet electronic configuration. Okay. Okay, let's carry on with question 2. So you have another table. This time around, you are given the name of the ionic compounds. You're supposed to fill up the subsequent columns on the corresponding cation, anions, as well as the final chemical formula of the ionic compound. Okay, so the first two has been done for you. So let's zoom straight into 2C, potassium chloride. Okay, so yeah, so in ionic compounds, you should already know that there are two components to it. So the first part is always coming from the metal, the second part coming from the non-metal. Okay, so here I'm going to draw you a skeletal structure of the periodic table, which you should be very familiar. Okay, roughly the staircase, the zigzag line is over there, and you can make good use of the group number to help you immediately get the charges of the cation, and anion, right? So for cations, group 1, group 2, and group 3 metals, it will be 1 plus, 2 plus, and 3 plus correspondingly. And then for anions, we'll work backwards. Okay, group 7, group 6, and group 5. So group 7 non-metals will form ions with a 1 minus charge, followed by 2 minus and 3 minus. Okay, so yeah, with this simple table to refer to, it's very easy for you to get the cation and anion with the correct charges. So for instance, let's say if we look at 2D, aluminum chloride, aluminium is in group 3, so it's Al3 plus, chloride group 7, so Cl minus. So over here, very importantly, you have to balance the charges. So if you look at Al3 plus, 1 unit of it will give you 3 positive charges. 1 unit of chloride only gives you 1. So at the moment, you need 3 times of your anion in order to balance the charges. So therefore, your final chemical formula is AlCl3. Then if you look at 2E, calcium chloride, okay, so again, using the quick method to help you, calcium is in group 2, it's a metal, so it will lose 2 valence electrons to form Ca2 plus. Chloride, on the other hand, or rather chlorine, is in group 7, so it will gain 1 electron to form Cl minus. Okay, yeah. So over here, again, 1 unit of your cation gives you 2 positive charges, but only 1 negative charge is there from 1 unit of your anion, right? So at the moment, you can see it's 2 plus versus 1 minus. You can only cancel one of them. So then the thing to do to balance the charge naturally will just be your simple math, right? You need 2 units of your chloride instead. So therefore, the final chemical formula for our ionic compound calcium chloride is CaCl2. Okay, let's move on to 2F. Alright, so we see zinc here. Zinc is a transition metal, so this is the one that you will need to memorize the charge, which is Zn2 plus. And then oxygen, which is from group 6, will form O2 minus oxide ion. So this is quite similar to the previous example. 2 positive charges, 2 positive charge and 2 negative charge. So in this case, it cancels out pretty nicely, just like that for potassium chloride. So here, not much manipulation needed. It's just technically it's Zn1O1, but we don't write the numerical value 1. So therefore, you see here the final chemical formula for zinc oxide is ZnO. Okay, the last one is a little bit more tricky. So aluminium is 3 plus, oxide is O2 minus, right? So this part is just a little bit more tricky in the fact that the math is not so straightforward, but we can make use of the concept of lowest common multiple, all right, of 2 and 3, which is 6. Okay, so for aluminium, we will need to times 2. Oxygen, we need to times 3, right, in order to get 6. So therefore, this is how we get Al2O3. Yep, aluminum oxide. Okay, let's talk about question 3 now. So over here, you're given the name of the substances, which are ionic compounds. You're supposed to give the chemical formula and draw the dot and cross diagram, right? Okay, so as usual, we should always work out the electronic configuration. That should always be our first step in terms of the so-called workings. Alright, so if you look at the metal component here, we're looking at sodium, which has an electronic configuration of 2.8.1. So it will lose that 1 valence electron to form Na plus with the stable octet now, 2.8. Chlorine, on the other hand, is 2.8.7. So it will now gain one electron to form Cl minus, which will then also have the stable octet of 2.8.8. Okay, so in this case, Na plus Cl minus, so it cancels out nicely. So our chemical formula is NaCl. So in our dot and cross diagram, we are drawing the ions here. So the cation Na plus as well as Cl minus respectively, as I've highlighted. So in my diagram, in this answer, as you can see, you should notice that should always check for certain features for ionic compounds. So number one would be definitely the square brackets and the corresponding charges on the top right hand corner. And then you should also notice that I'm using the different symbols here. Um, for the cation, sodium, I am using the cross symbol to represent its electrons. And on the other hand, for chlorine, naturally then I'll be using the dot symbol. Okay. For the anion, just be very careful because they are the ones that are gaining the electron from the metal. So you would therefore have to show this difference very carefully and clearly using the symbols. So you notice that's why over here, this particular one electron that chlorine has gained, you need to show the appreciation that it came from sodium. Therefore, you have to put a cross here. Okay, so yep, then that would be your full 2 marks for your dot and cross diagram. Okay. Let's move to question 2, which is calcium oxide. Again, you would notice that I'm going to bring you through the same steps with the electronic configuration. So calcium is 2.8.8.2. It will lose that 2 electrons to form Ca2+. Oxygen, on the other hand, is 2.6. It will have to gain 2 electrons to form O2-. So in this case, again, my charges balances out very nicely. So the chemical formula is CaO. In this case, on the worksheet, we only require you to draw outer shell electrons. So you notice on both diagrams, it will have the stable octet electronic configuration, right? Octet meaning 8. Again, you see the symbols, I keep to it very carefully. So X represents the electron of calcium and the dot represents that of oxygen. Again, to show the appreciation that these 2 electrons that oxygen has gained came from the metal, I have to use the cross symbol over here. Okay. Yep. Now let's look at question 3, which is potassium nitrite. So potassium is 2.8.8.1. Being group 1, you will lose 1 valence electron to form K+, cation. Then nitrogen is 2.5. So in order to be stable, it will gain 3 electrons to form N3 minus nitrite ion. Okay, so over here we need a bit of manipulation. So you notice that now if we look at 1 unit each of your cation and your anion, each unit of your cation, K plus in this case, only gives you 1 positive charge, right? But for nitrite, 1 unit gives you 3 negative charges. So over here, in order to balance the charges, I need 3 times of my cation. Therefore, in doing this balancing of charges, I'm having 3 of my cation, right? So therefore, the final chemical formula is K3N. So now we are ready to draw the dot and cross diagram. Again, this question, you're only required to show outermost electrons. Notice the same things. My valence shell, they are all stable octet. Symbol used, cap constant, right? Cross for potassium, and then for the 5 electrons of nitrogen in the valence shell, represented by the dot. The corresponding charges are indicated on the top right hand corner, surrounded by all these square brackets as well. And then again, notice these 3 electrons that are gained came from the metal, so we need to use the corresponding symbols. And most importantly, don't forget the coefficient over here, which will show the understanding that you have 3 units of your cation. Okay. Moving to question 4. So we have aluminium oxide. So similar way, we always start from electronic configuration. And in the previous part of the worksheet, we have already seen the process. So we know it's Al3 plus and O2 minus. And in terms of balancing the charges, we want to look at lowest common multiple of 2 and 3, right? So for oxide, in order to get to 6, which is the lowest common multiple, you need 2 times 3. And then for aluminium, it will be multiplied by 2 to get 6 plus, right? So then after that, 6 plus will cancel away with 6 minus. So that's how you eventually get Al2O3 as the final chemical formula for aluminium oxide. So then this, with this, we are ready to translate it into dot and cross diagram. And in this case, because there's no indication that we should only show outer shell electrons, so over here we are drawing all shells, meaning 2.8 for oxide and also 2.8 for Al3 plus. Okay, so if we look at my diagram, same thing. I keep to the same conventions of using the corresponding symbols, cross for aluminium and dot for oxygen. So for oxide over here, these 2 electrons that are being gained by the atom will need to be represented using the cross symbol. And you also notice I have square brackets and the corresponding charges. And most importantly, again, don't forget about your coefficients. So Al2 and then O3, 3 units of your oxide. Okay. Now let's look at question 4. We have a diagram that represents the arrangement of electrons in magnesium atom and oxygen atom. So over here, since we're talking about the element itself, we can definitely refer to the periodic table of elements. And if you look at part A, they tell you this is magnesium 24, so meaning the nuclear number is 24 and the proton number doesn't change, right? So it's 12 for magnesium. Oxygen, on the other hand, is oxygen 16. So 16 is the mass number, and the proton number of oxygen will be 8 if you just get it directly from the periodic table. Okay, then yeah, so proton number here, no issues. Then for the number of electrons, immediately you'll be able to know the answer is exactly the same number, right? Because referring back to the question, you know that this is talking about atoms. So our first relationship holds true here. Number of protons equals number of electrons. Neutrons, on the other hand, we use the second relationship. So we take the bigger number minus the smaller number. That's how we get the number of neutrons for the atoms. Electron arrangement is the same as electronic configuration. Use group number and period number to help you with this. B part 1, you're supposed to draw the dot and cross diagram of magnesium oxide. So again, the same drill. Work through the electronic configuration. You know that your cation that you're trying to draw is Mg2+, which is 2.8, stable octet. And then for oxide, it will be 2.6, gaining 2 electrons to form O2 minus. Okay, so this one is highly similar to the previous questions that we have seen. B part 2, explain fully in terms of the transfer of electrons and the formation of ions, the changes. Okay, this part you should box it up and highlight it together with me. The changes, meaning you need to talk about the initial and the final, right? Which occurs when magnesium oxide is formed from the respective atoms. So you see my answer, I am also structuring it in a very clear way. Okay, so I talk about the metal component first. So magnesium atom with the electronic configuration of 2.8.2 will lose the 2 valence electrons to form Mg2 plus ion. Okay, and this is so as to achieve the stable octet electronic configuration. The non-metal, on the other hand, oxygen, with an electronic configuration of 2.6, will need to gain 2 electrons to form from magnesium, from the metal, to form the O2 minus ion in order to achieve the stable octet electronic configuration again. Okay. Alright, let's look at the last two questions. Part C, using structure and bonding, explain why magnesium oxide has a high melting point. Okay, so these last two questions we are looking at physical properties of ionic compounds. So first one being melting and boiling point, and yeah, so we need to talk about both structure and bonding. Okay, so we start off by saying that magnesium oxide, ionic compounds in general, they have a giant ionic lattice structure. And as a result of that, when we heat it, we need a large amount of energy needed to overcome this strong electrostatic force of attraction that uh, that happens between the oppositely charged, in this case, Mg2 plus and O2 minus ions. Okay, so this is the bonding portion. So if you need such a large amount of energy to overcome the strong force of attraction, then it therefore results in high melting point. Okay. Part D, using structure and bonding as well, explain why molten meaning liquid state, right? In class, I shared with you, you can think of it as, let's say when you eat molten lava cake, right? You cut open that lava cake, it oozes out as a liquid state, right? Then, or if you think about molten lava, as in the one that comes from a volcanic eruption, same thing, it also is able to flow. So the word molten basically just means in the liquid state. So explain why magnesium oxide in the liquid state can conduct electricity, but solid magnesium oxide cannot. Okay, so over here you are trying to use structure and bonding to explain this difference in electrical conductivity, which is a physical property. So again, mention that magnesium oxide has a giant ionic lattice structure. So when in the molten state, liquid state, there is this presence of free moving Mg2 plus and O2 minus ions in this case, which can carry electrical charges. Okay. But in the solid state, these ions, they are held very strongly by the strong electrostatic force of attraction that is within the giant ionic lattice. Okay, so that's why in the solid state, there's no charge carriers in the form of free moving ions. So they are not free moving, they are being held tightly. Okay. Yeah, so this concludes worksheet 1 of chemical bonding, which covers all the concepts that is in ionic bonding. Okay, I will see you in the next lesson. Bye bye.